Welcome. So this is a continuation of previous lecture that was mechanics and we were solving the problems. So today I will start with a problem of a spring force problem. So generally there is a misconception between the students about the spring force. So this is a problem. I will start from this problem. Problem number one. So there are two springs having the spring constant K and there is a body of mass M in between. Question is to find equation of motion equation of motion for a small oscillation small oscillation along x direction, and the coordinate system is defined as like this is x and this is y. Okay, so this is basically a simple problem which we start from at any time t. So at time t is equal to 0, let us suppose that the given problem was like this, and at time t is equal to t, I displace this mass m by slightly in this x direction, and at any time t of motion the block will look like this. The bob will come here, that is mass m, and this spring will stretch like this. Now we have to write it equation of motion. So first let us assume that the natural length of a spring is your L. Spring is L. Okay, so the natural length of the spring is L, and at any given instant of time, let us suppose that this displacement is your x. Okay, so from Newton's laws of motion, we know that force is equal to mass times acceleration. And see, here I have displaced only in x direction, so I just need to write the force in x direction, that is Fx is equal to mass time acceleration in x direction. Okay, see, I have defined in only this Cartesian coordinate system, you can write the components as well. Okay, in polar coordinate system or in spherical coordinate system you cannot write that Fr is equal to some that times this. Okay, so in Fx you can write this. So that is your equation of motion basically. Now the task is to find the force. So basically this what misconception about the student is basically F is equal to Kx. That is the spring force generally written in books. But this, what about this x? This x is not just a displacement x. This is elongation or compression or compression. This is not simply a distance or displacement along that. So that was a misconception there. So here, what will be that x? We will see. See, the natural length was L, and when it was in motion, then the displacement along the x-axis was, let's say, x. So what is this distance called? Okay, so according to Pythagoras theorem, this will be xl square plus x square ki power half. Okay, so initially its length was L, and final its length was L square plus x square whole under root. Then the elongation will be under root L square plus x square minus L. So that is the net elongation of the spring. So while writing the spring force, see, I am drawing the free body diagram of that mass. So this is mass M, and one force F is acting on this direction and one force F is acting on this direction due to both the springs. And let us say that this is your x direction and this angle is theta and this angle is theta. Both angle are theta. So from here you can write that 2f cos theta is equal to net force, that Fx minus Fx, because the net force of this and this will be given in this direction. Okay, so this is the spring force. So from here you can write this F is due to spring. Okay, so this is 2 times F of spring force into cos theta, and this minus sign, that is equal to m. Acceleration is x direction, can be written as x double dot. So that is the basically equation of motion. Now we have to substitute it for a small oscillation. So this is finally the result of this. See, cos theta is a nonlinear function, and we have to substitute this equation for a small oscillation. And from graph you can find that cos theta is equal to x by under root of L square plus x square. So this equation of motion will become mx double dot is equal to minus 2. Spring force is k times under root L square plus L square minus L, that is the net elongation, k times net elongation, into cos theta, that is x by L square plus x square. So this will become mx double dot is equal to minus 2, that is under root, that is half. So this will be become 1 minus L by under root L square plus x square into x, and this will become 1 minus L square plus x square ki power half, that is minus half. And now let's just do the binomial expansion of this. So this is minus 2kx 1 minus, take this L square inside of this, then you will get 1 plus x square plus L square power minus half. So this will become minus 2kx 1 minus x square by 2L square, the binomial expansion. So this is equal to minus 2kx, 1 cancel out, this is minus x square by 2L square. This is 2kx cube by 2L square. This will cancel out. Sorry, this minus will become plus here. So this is minus. So mx double dot is equal to minus kx cube by L square, implies that mx double dot plus kx cube by L square is equal to 0. So that is basically the equation of motion for a small oscillation of this spring block system. So basically the misconception what about the writing the spring force in spring force, that is equal to k times the elongation or compression. So F of spring is always given by k times elongation or compression. Okay, so we solved this first problem. Now let us see the second problem. So this is your second question, where we have to find the equation of motion for this small oscillation, provided that the spring constant of each spring is k. So to solve this problem, so let us assume that the free body diagram, let us say that the particle is like here, and we say that this direction is your x, this is your y, and this is your z direction, or whatever you want to choose the convention. So, and if I displace this is mass, that's mass m, in x direction, so let us have that the displacement is along this x direction, then the force of this spring 1 will be in the this direction, that is k times x, because the elongation or compression here, if I stretch is inward, if I stretch this block M in this direction, then it will be the compression. If I stretch in the opposite direction, then it will be elongation. So spring force is basically k times elongation or compression. So this will be this. Okay, and let us suppose that these are other two directions. Let me write it here clear. Okay, so these are other two directions. Now we are making an assumption that these, this is basically not an assumption, but from diagram you can see that this angle will be of 45 degree, and the assumption is that when I suppose this is a mass m and this was the spring, and if I stretch this spring in this direction, the distance is x, then the displacement of this upper spring will be not perfectly horizontal, but there will be a slightly uh, downward shift and rightward shift like this. So it will come like this spring. We are neglecting this type of effect, the downward direction. So we are saying that this displacement is nothing but x by x cos 45, that is x by under root 2. Okay, so this displacement in this direction will be in downward direction, and that is x by under root 2 distance it traveled, and same for this spring also, this will go in this direction, that is x by under root 2 direction. So the force will be k times x by under root 2, and this force will be k times kx by under root 2 times. So from here the net force on mass m is equal to this direction, that is kx by under root 2, this direction, that is kx by under root 2, and there is a force, that is kx. Okay, so we have displaced in this direction x, and we got these three forces in these directions. Now we have to find the resultant of these forces. So kx by under root 2, kx by under root 2, and these angles are basically 45 degree. So the total force in opposite x direction, that is kx plus kx by under root 2 times, that is cos 45, and there are two such forces, so that is kx plus kx by under root 2 into 2 under root 2, this will cancel. So sorry, this is not here, this is under root 2 by under root 2, so this will cancel, so this is 2kx. Now the problem is like this: mass is m, if I displace in this direction x, then the resultant force of all three springs will be 2kx, and this is in opposite direction. So the equation of motion, if fx is equal to max, fx is equal to 2kx, and this is minus mx double dot, because the force is in another direction and the displacement is in opposite direction. So the net equation of motion is 2kx is equal to 0. So that is basically the equation of motion for this three block system, where there were three springs and one mass in between, and one of them were displaced in such a way in that I represented by the distance x, and another two was displaced. uh, we neglected the slightly change in left or right position, so we just have taken the downward or left downward or opposite shifts. So that was x by under root 2, and we calculated it. So this was the basically the equation of motion. Now let us have one more problem for writing the equation of motion. So the next problem is, so there are three blocks which having mass m1, m2 and m3 connected by a three springs having the same spring constant k. Now we have to write the equation of motions for these systems. So let us assume that the displacement of this spring first is in, that is x1, the displacement of the second block is x2, and the displacement of the third block is x3 from its mean positions. So initially the condition was that they were all in their mean position, and we displaced them by such directions. So the block m1 have displaced by distance x2, sorry x1, and block m2 was displaced by distance x2, and block m3 was displaced by distance x3. Okay, so that was the problem. Now for writing the equation of motion, see, we have to write the force. Okay, so basically the force on block M1 will be the spring force due to this spring and the spring force due to this spring. Block on mass 2 will be the spring force in this direction and spring force in this direction, and block on mass 3 the spring force will be in this direction. Now what I have told you that F spring force is generally K times elongation or compression. Using the compression, so using this concept I will be writing these equations of motion. So for, let us write for M1. Okay. Okay. So the net force, that is mx1 double dot. So this will be in this direction because I have taken x1 as positive direction. So this will be spring force of this minus spring force of this. So what is this force? This force is K times net elongation. Net elongation is x2 minus x1. Okay. And here the net elongation, see, this is fixed. So there is no change. So this is F x1 minus 0. So that is K times x1. So net force is K times x2 minus x1 minus of K times x1, because these forces are in opposite direction. So this force is acting in this direction and this force is acting in this direction. And I am writing this in this direction. So I have assumed that the downward direction is positive and the upward direction is negative. So this is the equation of motion for block M1. Now for block M2, let us write in similar way. See, first the acceleration, that is mx2 double dot, that is the net force on block M2, that is equal to, and similarly this is in this direction. So what is this force equal to? Or this force is equal to K times x3 minus x1, x3 minus x2. So that is the net elongation in downward spring, and the net force is K times x3 minus x2, and this force is basically given by K times x2 minus x1 because the elongation will be the same. So this will be equal to K times x3 minus x2 minus K times x2 minus x1. This force is acting in downward direction and this force is acting in upward direction. That's why this negative sign has been come here, because I have chosen negative as a upward direction. Now for block M3. Okay. So similarly, mx3 double dot, that is the net force in the of block M3. So there is only one force in upward direction. In upward I have taken is negative, so that is K times x3 minus x2. This force will be K times x3 minus x1. Okay, sorry, x3 minus this is x2. So these are the, and this force is acting in upward direction. So this is how we write the spring force in such a manner where various spring and masses are connected. Now we will solve a problem that was given in TIFR 2016. So let us have that problem. So this was the problem that was asked in TIFR 2014, where there were two blocks of mass 3m and 2m connected by two springs having the spring constant both k, and we have to find the frequency of oscillation of this block system. Okay, so let us solve this problem. Now assuming that the displacement of block 3m is x1 in this direction, 2m is x2 in this direction, and this is your fixed end. Okay, so mx1 double dot, that is 3 times m because mass is 3m, so 3m x1 double dot is equal to K times x2 minus x1 minus of K times x1. This we have solved just in the previous question. So this force is given by basically K times x2 minus x1. This force is given by K times x1 minus 0. So that is K times x1. So net force on block of mass 3m is k times x2 minus x1 minus. So this can be written as 3m by k x1 double dot is equal to x2 minus 2 of x1. Let us say that equation is 1. So this was for block of mass 3m. Now similarly writing the equation of motion for block of mass 2m. So it is simple because only one spring, so that is 2mx2 double dot is equal to minus of k times that is x2 minus x1. So 2m by k x2 double dot is equal to x1 minus x2. So we have find this equation of motion here. Now we have to find the frequency of oscillation. So basically we were from at this equation. So this equation can be written as m by k x1 double dot is equal to x2 x2 by 3 minus 2 by 3 of x1, and this equation can be written as m by k x2 double dot is equal to x1 by 2 minus x2 by 2. Now add these equations, what we will get is m by k x1 double dot plus x2 double dot is equal to, that is x1 by 2 minus 2 by 3 of x1, and the second will become x2 by 3 minus x2 by 2. So this is equal to minus of 4x1. This is plus 3x1, and this will equal to plus 2 of x2 minus 3 of x2 divided by 3 to 6. So this is equal to minus of x1 plus x2 by 6. So we came up an equation that is m by k x1 double dot plus x2 double dot is equal to minus 1 by 6 of x1 plus x2. So now let us define a new coordinate. Let us substitute s is equal to x1 plus x2. This implies that s double dot is equal to x1 double dot plus x2 double dot. So this equation will become, so m by k s double dot plus 1 by 6 s is equal to 0. So from here your omega is equal to under root of k by 6m. So you write this equation x double dot is equal to minus 1 by 6 k by m into s. So that is your frequency of oscillation. So omega square is equal to k by 6m. So omega is equal to this. So that is a new coordinate, that was x. So the oscillation, we are talking about the frequency of oscillation, that will be x1 plus x2. So this type of coordinate is called a normal coordinate. So let me define here one new coordinate, that is called a normal coordinate. Normal coordinate. When you will study the Lagrangian and Hamiltonian dynamics, or that equation of motion where we will be dealing by total energy and kinetic energy and potential energy, and you will find the equation of motion from there. So these terms come from there, the normal coordinate. So basically this is a new coordinate, new variable in terms of which coupled differential equation for masses reduced into equation of SHM. So this problem was there were two masses of 3m and 2m. They were coupled from a equation that were from coupled from two different springs having the same spring constant. So that type of problem is called coupled equation, coupled problem. So these types of oscillations are given by the normal coordinates oscillations. So for this problem, the answer should be under root k by 6m, and we have defined a new coordinate that is called the normal coordinate, and here it was the sum of both the displacement, that was x1 plus x2, and this is a new variable in terms of which coupled differential equation for masses reduced to equation of simple SHM. See that the acceleration of this block, the acceleration of s is equal to negative sign and this displacement is x. You know that when a is equal to minus of some constant a naught times x, so this equation is of equation of SHM. So similarly here a is defined by x is defined by s, so normal coordinates give you the equation of SHM here. Based on this normal coordinate problem, let us have one more problem that was asked in just examination. So the problem was, so this was the problem that was asked in just examination. So this was asked in just. So this is a coupled problem where two masses of mass m and m was coupled by three springs having the spring constant k. And if x1 and x2 are the mean displacement of mean position, so write the equation of motion, and second find the frequency of oscillation. See, the solution is given. I'm solving this equation. This end is fixed and this end is fixed. So the spring, the force in this spring will be, let us say that is x1. So this is k times x1, and this force will be k times x2 minus x1, because so how I am writing is, I will show you. See, this is your 0 and this displacement is your x1, this displacement is your x2, and this is fixed and I am representing by 0. So the force that is given by this spring, which will be in this direction and this direction, that is k times x1 minus 0. The force by this spring will be given by k times x2 minus x1. The force in this spring will be given by k times 0 minus x2. Okay, so that will be the force in all the springs. So this will be kx1, this force is equal to k times x2 minus x1, and this force is k times minus of x2. So I have written the force. Now let us draw the free body diagram of this system to write the equation of motion. So for block M1, so starting from block M1, so for block M1 or M, so let us call this block as 1, this block as 2. So for block of mass M, that is block M, so we have block of mass M. This force is acting k times x2 minus x1, and there is a force that is in opposite direction, that is k times x1, and the acceleration is in this direction, that is x1. So the equation of motion is mx1 double dot is equal to k times x2 minus x1 minus of k times x1. So that is your first equation of motion. And secondly, for block M2, so for block M, having this position second, see, this is block of mass M, the displacement is x2 in this direction, this force is k times of minus x2, and there is another force in opposite direction, that is k times of x2 minus x1. So mx2 double dot is equal to k of minus x2 minus of k x2 minus x1. So this force is equal to k times x1 minus twice of x2. So these are the two equations of motion which we have solved the A part of this problem, that was to find the equation of motion. Now we have to solve this equation. So let us suppose that this equation is 2. So for solution to find the frequency of oscillation, we should solve for normal coordinates. So let us add these equations 1 and 2. So add equation 1 and 2, you will get mx1 double dot plus mx2 double dot is equal to, if you add these, so x1 is 2 times, so that will become minus of k times, that will be x1 plus x2. You just add this, you will get, so this m is not here, so this is m of x1 double dot plus x2 double dot is equal to minus k times x1 plus x2. Now let us say that one normal coordinate is your s, that is given by, so for first let us say s is your normal coordinate given by x1 plus x2. So from here substituting, you will get s double dot is equal to x1 double dot plus x2 double dot. So ms double dot is equal to minus ks. So from here s double dot is equal to minus k by s. So this k by m is your frequency of oscillation. So omega is equal to under root k by m, that is your frequency of oscillation. So there is one more solution of this problem. So let us let us subtract, sorry, we have did addition. So let us subtract 1 minus 2. So what you will get, you just subtract it, then you will get m x1 double dot minus x2 double dot is equal to 3 times k of x2 minus x1. You will you just subtract it, you will get this equation. So from here you will get m x1 double dot minus x2 double dot is equal to minus 3k x1 minus x2. So now you have another normal coordinate that is substituted by x1 minus x2. So let us have another normal coordinate, that is t. Let us say that is x1 minus x2. This implies that x1 double dot minus x2 double dot is equal to your t double dot. So mt double dot is equal to minus 3kt, implies that t double dot is equal to minus 3k by m times t. So this 3t by m is your another frequency of oscillation. So here omega 2 is equal to under root 3k by m. So this omega 1 was k by m, this was 3k by m. So these are called the normal coordinates s and t. This s here and this t here are called the normal coordinates, and the frequency are under root k by m and under root 3k by m. This was asked in TF, sorry, just in, I don't remember which year it was asked, but this was the problem. So hope now you will get what are normal coordinates and how, what was the misconception and how to solve the spring force problems. So that was all about today. In the next lecture, I will start a concept on circular motion. So this was all about the Newton's laws of motion. Basically, the spring force, we have solved a spring force problem, drag force problem, mass pulley system. So that was enough for now. I would suggest you to solve more problems from Kleppner or from H.C. Verma, whatever book you write, whatever book you like. So if you have not subscribed the channel, please do subscribe the channel for latest update, and your comments are always welcome. Thank you. All the best.